3, 2, 1, let's go! I'm the host of the PBE podcast, Troy Tittlemeyer, sitting down, fortunate enough and honored to sit down at Microseismic Inc.'s booth 1409 at Image 2023 today. This is the second day. Yesterday, I learned a lot about the fundamentals of Microseismic through Dr. John McKenna's podcast, and we talked with the COO and president and kind of got the vision of what's going on at Microseismic. Now I'm equipped to sit down and finally dig in with Peter, Duncan, and Nader as they can introduce themselves here in a minute. First of all, what do you think of the show so far?
Oh, wow, it's been great. We've got a lot of traffic. We've got a great booth location. We've got some great people sitting on the floor with us in the booth. We got some really interesting technology out front, and people are stopping. They want to see what's going on.
That's right. That's why we're here. Please introduce yourself, Peter.
Well, I'm Peter Duncan. I'm the founder and CEO of Microseismic Inc. I started this company in my bedroom in 2003 to try to do passive seismic. Passive seismic, that's any kind of just listening to the earth. And we've done frac monitoring, and now we're moving into carbon sequestration monitoring and karst detection and things like that. We're having lots of fun using this intriguing science, which back in 2003 was brand new. People didn't know what it was, and now it's become something that's almost considered old hat. It's amazing. You get old and people think something that was new is now prosaic. But we keep innovating, and part of that innovation is this guy sitting next to me.
Right on. Nader, please introduce yourself.
My name's Nader Issa. I'm the CEO and co-founder of Terra 15. Started Terra 15 almost 7 years ago now in Perth, Australia, to commercialize and bring to the market a really new next-generation distributed acoustic sensing instrument.
Say it again, the acoustics?
Distributed acoustic sensing. It goes by the short acronym DAS in the geophysics community.
Okay, so this is getting us into the partnership. Let's rock it back a little bit, Peter. You got degrees. You figured out these technologies that were being applied in different ways, and in 2003 you said, hey, why don't we use some of this stuff that's out there for monitoring and microseismic level? Or how did the birth of this kind of go?
Well, you're right. We looked at the technologies that were around for acquiring data, and we said we can do things in the field without having vibrators or dynamite. We can solve certain problems, and over the years we have developed that technology. It was a bit of a different approach to analyzing data and what you're listening for. You can think of it as listening to earthquakes, but scaling it down to something that's appropriate to the oil field. And now we've branched out into different areas of utilization. But one of the things we've always been proud of, one of the things that we've always been diligent about, is trying to use the best technologies to apply to our problems. So we've never been in the business of making seismometers. We buy best of brand. We've never been in the business of making geophones. We buy the best of brand. And this technology that Nader's talking about, DAS, has come onto the market. Oh, it's old technology, but it's only now in the last few years started to become practical. And we realized there were applications of it in our business that would be better than geophones. So I spent some time, I went out on the market, the web, and I investigated all the DAS equipment that was available, and I came on this little company in Australia that had very little presence except in academia in North America. And I looked at their specs, and I called up Nader cold, and I said, Nader, how are things in Australia? And I think you might have a technology I'm interested in. And we talked, and it was a good conversation, and then went to bed for about 6 months. Market wasn't there. And then things started to heat up where it was appropriate, and I called him again, and I said, Nader, it's me. And he said, I remember you. And I'm going to be in Houston in a couple of weeks. How about I come and see you? Up. He came in, we sat in the conference room. I really liked what they were doing. I really liked some new things they'd done to their interrogators since I'd first talked to them. And I said, I think we could work together to bring your technology to North America and blow this market apart.
Whoa. Wow.
Yeah.
That's kind of that. Is that accurate? Was that?
It's accurate. Yeah.
Don't say I'm lying.
No, it's very accurate. And actually, we're really honored and excited to be working with Microseismic, very well-renowned company in the field. Actually, made an industry in this energy sector, and it's a great privilege to be working with them. It's a sector that we generally don't work in Australia. We work in other sectors, typically mining and utilities. And we've always been on the lookout for the best team and the best partners to work with to get into the oil and gas and the energy sector and a lot of these other applications that are really big in North America.
Right.
And so here we are today.
Wow. And what's your background? What kind of degrees do you have? How did you do this?
I'm a physicist by background.
Oh,
I got
nice.
a PhD in fiber optic technologies
Really?
from the University of Sydney. Started in 2001, graduated 2005. So I've been working with fiber optic technologies for almost 23 years now.
Man.
I did spend about 4 years of my career as a passive seismic geophysicist. I wanted to try something new and reskill in a new area. So I talk the talk. I understand the jargon, but I'm nowhere near as accomplished as a geophysicist and a geoscientist as the team at Microseismic.
Man. Yeah, so the idea of fiber and on all this, I kind of remember the horizontals, and in 2014, 2015, 2016, we were drilling these things in the Permian Basin, and it was always very difficult to get a straight answer on where do we think most of this fluid's really coming from in the horizontal well, right? You frack the whole thing, but in the reality of it, certainly after 100 days of production and you get further along in the production, where's it really coming from? And I remember fiber being an option. It was expensive, right? Back then anyway, and the option was run fiber down it, and maybe it could tell which perfs or which stages are contributing the most fluid, and maybe you'd even be able to tell this one's mostly brine based on its temperature, this one's mostly oil coming through. Like, it was fascinating what fiber could feel or listen to, however you want to say that. Now I'm getting with Microseismic yesterday, talking with Gary and your whole team that has been doing Microseismic for so long. They're like, fiber is going to be down all the pipelines, the electrical. This building could be, a future building of this size can be built with so much more technology, subtly laid out in the infrastructure. You're already laying all those lines. You're just now laying another one, and now you for forever, ideally, you know where the leaks are coming from. You know where your problem's at. Like, you know where it's at because of fiber and this technology that could listen really well in the infrastructure. And to me, I was just blown away. My mind just started thinking of future cities, and you know what I mean, 20 years from now, 50 years from now, what does it look like? So before we get there, how did this partnership, I get it, you found them, you did the research, you know what you're doing, you got Microseismic, you got 20 years experience, now we're applying it to carbon sequestration and everything else. What's the nuts and bolts of this partnership that you guys are announcing at Image 2023?
So, a big piece of a developing piece of our business, it's not big yet, but it's a developing piece and it will be big, is this carbon sequestration. And in the carbon sequestration, the one of the prime goals is to make sure we don't have any induced seismicity, any earthquakes caused by the injection of fluids, because the injection of wastewater has caused a bunch of induced seismicity. But beyond that, we want to make sure that we know that the cap rock that we're putting the fluid underneath is remaining intact, that we've not got any leaks, and we want to make sure that the plume, as it grows, doesn't round around the edge of the reservoir and start leaking up to the surface. Well, all of those things we can detect by hearing very small noises. We like to deploy a large area array of geophones to listen to those little sounds. But the problem is it's a large area on the surface, it's a long way from where the fluids are. And we like to get it calibrated. When we're doing frac monitoring, we can calibrate our data with the fracs themselves, or with the perf shots that make the holes in the pipe that the fluid then is ejected through to stimulate the well. But with carbon sequestration, we don't have that advantage. But we can put a fiber down to the very top of the cap rock, and it's very sensitive. It can hear very, very small noises, and we can use that to calibrate what we're hearing on the surface. So using that calibration, we can now make the geophones on the surface be very, very much more effective at hearing those small sounds and solving the problems, the three problems that I just talked about.
Right. That's fiber. Fiber's doing that. Okay. And you've been able to make it cost effective, possible in today's environment.
That's right. I mean, it's the cost question has been something that we push against regularly. There's a cost curve to any technology. Fiber optics used to be very expensive in the early days, but today it's very cheap and quite ubiquitous. It's everywhere. And then if you talk about new instrumentation and new devices to do sensing using optical fibers, as the applications, as the volumes and the use cases grow, that technology comes down along the cost curve, and the applications open up, and you can use it in more and more places, applications that you never thought about before. And that's the vision we have for distributed acoustic sensing, DAS. We see ourselves in an era where large sensor counts are going to be part of everyday business. You're not talking about a few sensors here and there to monitor things. You're talking about thousands, hundreds of thousands, potentially even millions of sensors monitoring infrastructure, monitoring our daily activities, our daily lives, the assets that we rely upon in modern society. Now, to do that, the cost per sensor needs to come down, and that's exactly what DAS does for you. The cost per sensor is by far much lower than anything else you could achieve when your sensor counts are in the hundreds, thousands, or beyond. But data by itself is not as valuable as what you do with the information that data reveals for you. And so what you need to provide is you need to create a solution, some sort of actionable insight for the end customer based on the data and the large volumes and quantities of data that you can collect these days. And that's something that Microseismic has a very long and proven track record in, and so it's a very exciting partnership.
So Troy, I'd like to respond to something you said earlier that really resonates with me, and I think you'll find this interesting. You were talking about cables that are everywhere.
Yeah.
You could put them on pipelines, you could put them around on the ground. Well, Nader's got an interesting story on this, but first I'll tell you about the group out in Stanford University who used the fiber optics from telephone wires, AT&T, stuff that they didn't lay, it was there, and they borrowed one of the strands of these telephone wires, and they listened to the earthquakes going on in the San Andreas Fault. The little tiny creeping sounds as the San Andreas moved. Now, talk about cost effective. They didn't have to lay out anything in the ground, it was already there, and they just hooked onto it with an interrogator and then listened to the sounds. Nader, you've got a great story on that.
Yeah, indeed. So we generally use existing optical fiber infrastructure that's in the ground. We find fiber that's co-located to pipelines, especially, including the water infrastructure in cities. And we use that optical fiber to monitor those pipelines on a 24-hour a day basis, 7 days a week, notifying about leaks, construction activity, anything that could be associated with the management and maintenance of that pipeline. Now, those are just a few of the things that we can measure and monitor with these fiber sensors. There's earthquakes that we're detecting from all over the world. There's traffic. There's there's what's happening in the subsurface, all of which is rich and in the data. Just needs to be tweezed out.
What you referred to the interrogator? What is that?
Well, the interrogator is I shouldn't be answering this. You're the scientist. Go ahead, tell them what the interrogator is.
So that, simply stated, that's the box that you connect the optical fiber to. It houses all the optics and the electronics, like the lasers, the detectors, the amplifiers, the digitizers, even the computing processor that churns through the data in real time. That's all housed in one physical box, and that's called the interrogator because it interrogates the optical fiber. It sends light down the fiber, pulses, thousands of pulses per second, and it receives the backscatter of light that comes from the tiny imperfections that are present in optical fiber from the manufacturing process. All fiber has these imperfections, millions every meter, and so when you send a pulse of light down the fiber, you get a reflection from every single meter, which is like a fingerprint of that meter, of that meter of optical fiber. And every meter has its own unique fingerprint, as the fiber stretches, you track how that fingerprint changes on a millisecond basis or faster, and you can extract strain from that, strain rate information.
So, Troy, do you have a child?
Yes, 3 of them.
Did you get an ultrasound? Did your wife get an ultrasound?
Yeah.
So with an ultrasound, The doctor sends a little ping down and gets the bounce off the baby, and it does it all over, and it gets a picture of the baby.
Right.
So what an interrogator does is send a pulse. It's now light, not sound, so it travels faster, and it's higher frequency, more resolution, but it goes down and it finds that reflection where something's happened on that fiber, and because it's contained in that fiber, instead of it just being the belly of the woman, it can be anywhere in the town. It can be anywhere where that fiber goes, and it hears the little reflection, or it sees the little reflection as a result of a disturbance.
Whoa.
It times when it comes back, and it can says, oh, there's something there. There's something there. I can put it around a building, and if an intruder steps on that point, his reflection comes back from that point and says, there's an intruder right there. Go get him, guys.
Wow.
And so what sold me as much as anything is the specs is that Nader showed me a little application he had on his cell phone where he was monitoring the water beneath a city in Australia.
Okay.
And it was all green. And it was all the AT&T cable, not AT&T I suppose, but it was all the telephone cable underneath the town. It was all green except for a little red dot. And that little red dot said there was a leak.
Wow.
And that application was in the hand of the water authority in that city. And that's exactly what we do. We have an application that we give to our clients that says where the red dot is a problem. Now we do it with a lot of geophones and a lot of sound, and it takes a lot of time. He's enabling us to do that better, faster, and easier.
Wow. Man, that's pretty exciting, huh?
It is exciting.
Been around for 20 years. You've been in the weeds of all this for so long, and now you're seeing fiber.
Able to do what I want to do better and faster and cheaper.
Damn, man, what a pitch. What a pitch. All right, doctor me up a little bit on the idea of fiber. Like, what was before fiber and what is fiber? Like, give me just some basics of fiber optics.
Fiber optics. So,
how many hours have you got?
Elevator
I've got a
pitch.
PhD in this subject. I could talk for hours on it. Fiber is basically glass. It is ultra pure glass that's manufactured through a synthetic process, and it's got some sort of chemical structure inside the glass that allows it to trap light. And the reason it has to be very pure is because it needs to be highly transparent. So if you take a piece of your window and you look at it from the side, it all looks green. You can't see through more than a meter of glass in a typical window pane. Well, optical fiber is so transparent that you could, if your window is made out of that super pure glass, you could see for kilometers through that glass with only a very, very small attenuation of the light.
Where did it come from? Like, who thought of this?
Yeah, that's a long story. I mean, there's history of people using waveguides like this back to ancient Egypt, but it was really in the 1960s and 70s that they found a way to purify glass and manufacture glass in such a way that it could enable the transmission of light over long distances.
Wow.
Prior to that, there's a famous quote that goes back to the 1930s where somebody, I can't remember which telecommunications company, said glass fibers will never be used for long distance communication. Well, now it is the primary conduit of long distance communication.
Yeah.
So Troy, if you go over to that booth right over there, you will see that they make a streamer that goes out behind boats, a seismic streamer. And down that seismic streamer, which is a long continuous cable that's maybe 3 inches in diameter, there will be a geophone every 12.5 meters.
Okay.
And in that geophone, what happens is there's wire in between.
Yep.
And the wires in between carry the signal that's generated by that geophone back to the mothership where it's recorded as a seismic record.
Okay.
But those samples are every 12.5 meters.
Right.
Only where the geophone is.
Yeah.
Now, replace that with a piece of fiber, and now we have a geophone every few inches. Anywhere that we can sample that there's been a disturbance in the cable, a strain on the cable. So that's the big advantage of fiber, is that instead of having a sample every 12.5 meters or every 50 feet or something like that, we can have almost continuous, almost an infinite number of samples. And in any science, any observable science like us, the more data the more accurate you are,
Yeah.
the finer the sampling, the better your image, and that's what that brings to us.
Right on.
Also
And it's
wanted to-
cheaper.
Yeah, and there's another important factor, which is glass and the fiber cables that you can buy are extremely resilient to harsh environments. So you're talking about high temperatures, easily to up to 80 degrees, 150 degrees Celsius, 300 degrees Celsius. I'm not going to try and convert that to
Fahrenheit.
Fahrenheit in my head.
No, that's freaking
chemically
nuts.
resistant in many respects, depending on the coatings that you want to use, and also immune to electromagnetic interference. So you may have high voltages, high currents, electromagnetic
affect
waves. It does not affect the signal whatsoever. So it's actually a very, very robust material to create sensors out of.
Can fiber measure EM anomalies?
Well, not really. It's immune to interference, so it makes it difficult to measure it. But the advantage is that you're not influenced by it.
Yeah.
If you've got a mobile phone tower nearby, it's not going to affect your measurement whatsoever.
Yeah. Wow. Man, I'm excited. So again, I was talking yesterday and getting a better idea of the Terra 15 and the kind of this merger and this idea of fiber and applying it to what we do. Carbon sequestration, karst identification, geothermal now, and oil and gas is the backbone of a lot of this. Applying this it just makes great sense, and it's exciting. For the younger generation and for the older generation, like this is something that is exciting, never been done before, and it's cheaper. This is where it's going. You guys are riding the front lines of this. You're on the razor's edge. I always talk about that. And if you're not on the edge, you're taking up too much space, You guys are riding that edge in technology and applications, and I'm rooting for you guys. I'm super excited to hear more about this partnership. I hope you guys write papers. I hope you give a lot more talks, because I want to learn everything about this.
Thank you. Well, we're excited too. Confucius said that when the student is ready, the teacher appears. It took us 20 years to get ready, and now my teacher is here, and we're bringing that technology to our business.
Man, right on, Peter. Thank you. Nader.
Thanks for the intro.
Thank you. Man.